Thank you very much for the kind introduction. And I would also like to thank the organizers for giving me this opportunity to share some of the thoughts and the things I've been working on. So, without further ado, let me share my slides. Can you see my slides?
Yes, sir.
Okay. Okay, so in today's talk, I'll be presenting some of the things that we have been working on in the area of model-based as well as data-driven techniques for tackling issues in energy and environmental impact optimization, and especially focusing a little bit on the issues pertaining to uncertainty. Uh, the rise in fuel prices is not any news for anybody here. We've been experiencing this throughout the globe. And as you can see, the gas prices are rising and still expected to rise further. The energy price cap in the UK has increased around threefold, from £1,000 to around £3,500 in last 2 years or so. And it is not news for anybody that the world is getting warmer. The implications of the increase in the temperature around the globe are pretty clear. We see more floods. We see, disasters happening in the area of climate and so on. So with all these, problems, where are we heading? And what
recording in progress?
What can we do as chemical engineers? I see that your screen sharing is paused. Is that true?
No, sir. It is.
Okay. Okay. There was an additional message on my screen. Okay. So I'll continue talking. So, with all these problems that we have at hand, obviously, there is a drive to move towards renewable energy, such as biomass and solar cell. And we have to make that transition at some point of time. But while we are transitioning to that stage where we are not dependent on fossil fuel anymore, there is still some time to go. And what I'm going to share today are some of the techniques on how do we work around optimizing the energy consumption and minimizing the environmental technique for the currently operating plants, which sometimes include fossil fuels and could include power generation plants based upon renewables. So my focus will be mainly on modeling and optimization techniques, and also trying to introduce some appreciation of the fact that we need to take into account uncertainty. Now, uncertainty is an issue that is something which is highly highlighted in the Institution of Chemical Engineers UK. Although it is an international organization, it is although based in UK, and they make a big point about this, that we should incorporate that into educating our undergraduate and master's students as well. So uncertainty is not just a research topic. It is something that our undergraduates should be able to appreciate, and when they go and work in industry, be able to apply some of the techniques that they learn while being educated in the university. So with all these problems at hand, how can chemical engineers help or other engineers help? So the two things that come to our mind is that first is that reduce the environmental impact, okay, and reduce energy consumption. By energy consumption, that can be translated into money as well, and say, in other words, reduce cost or increase profit. So if somebody is operating a business, that business could include, costs associated with the buildings, heating of or cooling of the buildings, and even operating the chemical plant they own. So eventually, by reducing energy consumption, they would like to reduce the cost or increase the profit. However, if you look at these two problems, which are reducing the environmental impact and reducing the energy consumption, they are sometimes looked at in isolation. Okay, so people develop really highly, let's say, promising techniques for reducing environmental impact. But is that for free? Is the new technology going to be more expensive than the technology that we already have? Or if we try to reduce the cost, can we do it without impacting the environment? So, this is some of the things that we'll discuss in the next half an hour or so. So, where I'm getting with this is that, is there a trade-off between cost and environmental impact? Are these two linked, or can we look at these in isolation? The second question that I would like to discuss today is, how can we address it?
Excuse me, sir.
Yes.
So slides are not moving.
So what can you see right now?
Second slide we are seeing.
Okay. So that's what I said earlier, that your screen sharing is paused, was the message I was getting.
Yeah.
So I'll stop share and share it again. Okay.
Oh, yeah.
So can you see my slide, which says how?
Number 5.
We
Sorry?
can see it, but presentation mode, sir.
Yeah, I'll put it in presentation mode.
Yes,
Is
sir.
it available now? Visible now? How chemical engineers can help?
Yes, sir, it's visible.
Okay.
Thank you.
Okay. So as I was talking about the interaction between the minimization of the environmental impact as well as minimization of the energy consumption, are these two things linked? And if they are linked, how can we address it? And most importantly, something which I alluded to earlier on about incorporating the impact of uncertainty in undergraduate education is, what if the forecast is not accurate? Okay, so we can make some plans now, take some control actions, but can we just set on an auto mode and assume that they will be optimal for the next week, year, decade, and so on? Okay, and if not, how can we incorporate those in our decisions? Just to give you an outline, in today's talk, I'll be focusing on computational modeling for optimal decision making. And three things that I'll be looking at are will be the first principle based models for making decisions, and then the second one, which is becoming quite trendy in chemical engineering as well, which is artificial intelligence and machine learning. So these are the data-driven approaches, and we are nowadays talking about digital twins of various engineering equipments that can help us, operate them even in a more efficient manner, design, and so on. And finally, the incorporation of uncertainty into our decisions. These uncertainties come into our models from a range of factors such as demand change, supply change, the change in the costs and profits of the materials that we are buying and producing, and also the regulatory framework, which is something which we usually do not look at very rigorously in our curriculum. But this is becoming important as well. because that even if you make some decisions, but they are not approved by a regulatory framework body, those decisions will not be implementable. So we need to take all these issues into account. So I will start by showing you a small or a simple motivating example to motivate the need for a model-based multi-objective optimization problem. Then I'll move into data-driven modeling and optimization techniques and focus mainly on refinery optimization using artificial neural networks. And the third topic I will touch upon will be a multi-objective optimization under uncertainty. And then I will show you there how we can take into account trade-offs as well as uncertainty, and finally conclude with some remarks. Okay, so let's, we have been operating refinery for several decades. This is an illustrative example, let's say, where we have two crude oils, crude oil 1 and crude oil 2, being fed to the refinery. There are some economic information available in terms of the cost price and selling price of raw materials and products. There is some technical information available in terms of what are the percentage yields of the two feeds or raw materials, some further economic information in terms of the processing cost, and some information on the inequality constraints in terms of how much we can produce for these three products. Now, I'm not going to go into the details of how we can, put it into a modeling framework, but let's assume that with this information, we come up with a linear programming model where we want to maximize the profit subject to the information given on this slide. And this results in a linear programming problem. Now, for a fixed feed information that we currently have and the fixed maximum allowable production information that we have, if we solve this optimization problem, we will come up with one answer. And that answer would be, okay, we need to buy so much of crude oil 1 and so much of crude oil 2, and we will be producing so much of these products which will satisfy these constraints, okay? Now, these constraints are subject to uncertainty, okay? They can change with time. They can change with demand. They can change with the local regulations that where the refinery has been set up. And let's say there isn't some uncertainty in the gasoline production expansion. So I'm showing on this graph or on this figure is how much gasoline production expansion can change. Let's say from some value, a lower bound to an upper bound on top of 24,000 barrels per day that we can produce. Similarly, there is some uncertainty on kerosene production expansion. So there is a further expansion of kerosene production in addition to the 2,000 barrels which are being produced per day. So this is our, let's say, rectangle or square of uncertainty. Now, subject to this uncertainty, now this uncertainty is not a fixed number that can change over a period of time. And if I want to figure out what my profit will be for different values in terms of the expansion that I can do for gasoline and kerosene, I need to even, essentially solve infinite number of problems that lie within that space. That is sort of a very brute force approach, okay? So what we have been doing here in our research group is that to not go down this route where it becomes impractical to find an optimal solution as the value of uncertainty changes as a function of time or due to other factors. So instead of solving, let's say, infinite number of optimization problems, we reformulate it as a multi-parametric programming problem and end up solving only two optimization problems. And that splits this space of uncertainty into two regions, region 1 and region 2. And these are known as critical regions. And profit is a function of gasoline production expansion and kerosene production expansion. And also the amount of crude oils that we have to buy are simple expressions of these two uncertain parameters. And these uncertain parameters are described by a set of inequality constraints. So these constraints taken together will define this region 1, and these constraints represent this region. And the profit and the raw material flow rates in this region are given by these expressions. It is not really important to actually look deep into what these expressions are. The key message here is that for dealing with uncertainty, there are certain techniques available which allow us to be able to solve these very efficiently and address uncertainty while we're designing and operating a chemical plant. Okay, so that is the key message here. And I'll be coming back to this message in a bit more detail when I'll be looking at multi-objective optimization as well as uncertainty in my last case study that I will present. Okay, so the key message here is that there are techniques available for dealing with uncertainty when we are designing and operating chemical plants, and that allow us to be not stuck in a situation where we are expected to solve millions and billions of optimization problems to find a solution. Okay, so now moving on. Okay, we have figured out more or less how we deal with uncertainty without going into the details of the solution technique. What if we have to also deal with the environmental impact that I mentioned earlier on? Now, just to give you sort of just a brief overview, environmental impact can take into account several things. It could be the global warming potential, acidification potential, eutrophication potential, and so on. And there are established techniques for addressing this, and there are established metrics for addressing these problems. And I'm not going to go into the details of those. There are things such as life cycle assessment and so on. The objective is that we would like to minimize environmental impact. And I'm going to go with the assumption that a suitable metric for environmental impact has been established, which takes into account these factors. One can argue that one would like to give a higher weightage to GWP or a lower weightage to acidification potential and so on. Okay, so that's a separate discussion, that which of these is important. Do we take only one of these criteria into account, or we take a weighted sum of those, and then what should those weightages be? So leaving that discussion for another day, let's assume that environmentalists or people working in the environment in the area of environmental impact have identified that metric, and these are the environmental impacts of the materials that are being are in the refinery we are looking at. Okay. And now we're not only just interested in maximizing the profit, but we're also interested in minimizing the environmental impact. So this leads to what is known as a multi-objective optimization. So what I would like to do is minimize the cost and minimize the environmental impact. So essentially, I would like the cost to go to zero, and I would like the environmental impact to go to zero as well. And this leads to what is known as utopia, which actually is sort of a hypothetical situation. We can not have zero cost and zero environmental impact. So the short answer to the question on the slide, can we reduce cost as well as environmental impact to zero, is no. And what we are essentially limited by is this curve, which is also known as a Pareto curve or a non-inferior curve, which essentially limits us to be able to find a solution on this side of the curve. So what this curve is essentially saying is that if you're trying to find a point on this side of the curve, that is just not possible. What we are going to find is a point on this side of the curve, or at best on this curve itself. Okay, now let's assume that we are able to find a point or a number of points on this curve. And this is mainly the objective of solving a multi-objective optimization problem, where we would like to obtain this curve so that we can present this to the management, to the government, to the local bodies, so that they can make a decision. And what this curve actually shows us, and it's a very informative curve, is that if you would like to reduce the environmental impact, and as we try and do that, you can observe that the cost begins to increase. And if you try to reduce the cost, the environmental impact begins to increase. So you cannot have a situation where you increase, where you decrease both of them. Okay, so there is a trade-off, and the objective as a process engineer for us is to be able to obtain this curve. And I will demonstrate this for the refinery problem that I mentioned earlier on. So here we obtain this curve, which shows that on the x-axis I have profit, and on the y-axis I have environmental impact. And what this curve shows is that instead of cost, I have profit here. So in an ideal world, or in a utopian world, you would like to have zero environmental impact and infinite amount of profit. But that is just not possible, because we are limited by this curve. And we obtain this curve by Pareto curve by solving a multi-objective optimization problem of the form that I showed you earlier on. So as we try to increase the profit, the environmental impact begins to increase as well. As we try to reduce the environmental impact, which is on y-axis, the profit begins to decrease. So there is a very strong interaction between the two. And this is something we should always keep in mind when we are looking at these problems, that we should not look at these in isolation. Okay, we understand that qualitatively, but to be able to represent that in a quantitative framework is important as well when it comes to making some real decisions when you're designing or operating a plant. What is also important to understand is that again, I have profit here, and the environmental impact is shown by this curve. But I'm also showing the impact of these decisions on how the amounts of raw materials and products that are being produced will be affected. Okay, so it impacts everything. And instead of profit, if I look at environmental impact, and I have a profit curve here, how the flow rates of the different raw materials and products are impacted as we make different decisions is also important. I'll quickly go back to the curve I showed you earlier on. So in real life, we will have to make a decision which will be just a point on this curve. Okay. The important thing is for us to be able to identify this curve and then discuss with the local authorities and plant operators that where exactly we want to operate. Okay, that is another discussion, but to be able to facilitate that discussion, it is important to be able to identify this curve. The next thing I wanted to discuss is what is quite trendy nowadays is the digitalization. And I'll do that through an artificial neural network approach for refinery-wide optimization problem. So, I briefly described the oil refinery earlier on. That was a simplistic representation, but actually, and it was a linear model. But in real life, an oil refinery operation, its design, its modeling is much more complex. It involves several operations which are highly nonlinear. And we face a number of challenges. So I represented a case where I had crude oil 1 and 2, but you could have several choices of crude oils, and that you would like to decide in what proportion they should be mixed. what should be the operating parameters for your plant, and there are several technologies, not just a simple box that I showed you earlier on throughout the oil refinery. And obviously, there is a lot of uncertainty in the operation of a refinery. There are several decisions to be made in terms of what is the optimal mixture of crude oils, optimize the gasoline and distillates blending, optimize fuel consumption, minimize losses, and there are some, let's say, binary decisions as well, that which units should be shut down, which should be operated. So it's like a 0-1 decision. And also, there are certain constraints in terms of ensuring that the temperatures don't go beyond what a catalyst can tolerate, and so on. So this is a very complex operation. What is currently, or has been the state of the art, has been to model these through a linear programming model. And this does not take into account the highly nonlinear interaction and nature of the various unit operations. And one of the reasons for this is that if you try and model all these operations in a nonlinear modeling framework and try and optimize, it is almost impossible to solve that optimization problem because it is too big and too complex. So what can we do? What we can do is first decide upon the type of refinery we would like to optimize. Obviously, if you start with a simplistic refinery, the problem is much simpler. But as we keep on increasing the complexity of the operations that are incorporated in your refinery, the problem becomes even more and more complex. But there is an advantage that the more the complex the refinery is, there is more chances of increasing the profit because you're producing highly valuable products as you increase the complexity of the refinery. So with the increasing complexity of the plant or the refinery leads to even more complex and complicated operation of plants. And as I mentioned earlier on, that leads to problems which cannot be solved even to feasibility, forget about optimality. So what we can do as chemical engineers or chemical process engineers, one of the approaches that we can do is use a data-driven approach. What does that involve? It basically is a technique where you look at some of the input data. This could be data that you can generate in a process simulator or that you collect in a refinery and correlate it with the outputs. Okay. So a simple case is, if you have some crude oils coming in and you're producing certain products, can you correlate the relation between the input and output? Now, the disadvantage of this approach is that you lose the physical insight or the meaning of what is actually happening in each of these plants or units within your big chemical plant. But the advantage is that this leads to simpler representations that can be incorporated into a more complex optimization framework. So simply speaking, what a neural network or ANN or artificial neural network does is that it provides a mapping of input data, which I represent by X, to the output data, which I represent as U, and we obtain a correlation that U is approximately equal to and function of the input. Now, this symbol approximation is important because it is an approximation. It is not an exact representation, but it is good enough for finding the optimal solution. And once we have found the optimal solution, we can go back and put it into the rigorous simulator and check whether the solution we obtained is indeed sensible or not. So we have developed this approach and implemented it on a refinery where we looked at various feeds and various products for various process units and correlated the inputs to the outputs. So this is a typical refinery model, which you would put in a process simulator, and we have replaced it by various neural networks which represent the models for these individual units. This leads to a faster real-time optimization of the refinery, and we can make quick and optimal decisions so as to satisfy various constraints as well as optimize various objectives. These graphs show the how the fits are or how good the fits are. So, for example, here the red curve is our prediction, and the blue curve is the output from a rigorous process simulator. And as you can see, they match pretty well. So for most of the cases, our predictions were pretty good. Here, there is a little bit of discrepancy. But as I mentioned earlier, we go back and check these answers in our rigorous simulator once we have found the optimal solution. And the idea is to be able to, predict the profit or calculate the profit for a particular refinery. Here is an example of two different crude oils which are being used to produce these products for a given information about the economics of the plant. And this is an example of optimization of the operating condition where these were the conditions at which the plant was operating currently, and these are the conditions at which we found that the plant should be operating. So if you see, there are some minor tweaks here, but this leads to a significant increase in the profit from $45.9 per ton to $48.5 per ton. So, you can imagine for a large refinery, this is a significant saving on an annual basis. So, as I mentioned earlier on, there are several challenges for the refinery. One is this, which I mentioned earlier, which was the optimization of the operating condition. But there is also an issue in terms of finding an optimal mix of various crude oils. So over here, we looked at 4 crude oils which can be purchased, and the optimal solution turns out that we should be operating or processing these 2 crude oils, and this was obtained by solving a complex nonlinear optimization problem which incorporates a surrogate model based upon artificial neural networks. Now, these type of optimizations were not possible because earlier people used to look at this from a very simplistic linear programming type of approach. We have looked at these complex modeling and found various optimal solutions, and these have been validated as well. Now, just to summarize, so what a refinery-wide optimization approach that I presented here does is that we are typically using process simulation software, which represents the representation quite well, but is not useful if you're looking at an optimization of that plant. And there's a lot of data which is collected in the plants, but is usually archived. Nobody uses it. But by using the approach that I just described, we can optimize energy as well as cost in the operation of refineries. And this technique is not just for refineries. It's quite generic technique and can be used for other processes, including chemical as well as energy plants. Okay, now I'm coming to my third and final topic, which is multi-objective optimization under uncertainty. So I started with a simple refinery example, which incorporated linear programming and its effect and how it is affected when there is uncertainty and when there are more than one objective function, such as cost as well as environmental impact. So the final example I'm going to look at is the power generation plant, where we have a fuel and it boils the steam in a boiler that goes to various turbines and valves to generate power, and which is over here, and then various and steams at various pressures: low pressure, high pressure, and medium pressure steam, which is sold or used in the process plant. I'm not going to go into the details of how this model was developed. I have a list of references at the end, and it describes the various factors. But just for the sake of completeness, we used a model which was published in the literature, and used the economic information that came along with it. Our contribution here was that the incorporation of the fact that typically what is done in the literature is they're just looking at minimizing the cost, but we also looked at minimizing the environmental impact and also the effect of uncertainty in power demand. So these two things were new. So this leads to a first principle model that I've shown here, which again is a linear model. And what we have done here is, so this is the uncertainty, θ1, in the generation of the with power or demand of the power. And this θ2 is the other second objective function, which is the environmental impact. So we reformulated this optimization problem, which involves two objectives: cost and environmental impact, and how that solution will behave when uncertainty is present in the system. So by solving this problem using a multi-parametric programming approach, which I'm not going to go into the details of, we obtain 4 critical regions in the space of uncertainty θ1 and the second objective function θ2. So there are 4 critical regions. So remember the first refinery optimization problem where I showed there were 2 regions when there was uncertainty in the demand of gasoline and kerosene. Now, in this case, I'm treating the second objective function as an uncertain parameter. And that allows me to obtain a full mapping of all the optimal solutions. So this is how the uncertain space is partitioned, and this shows how the cost, which is on the z-axis, is a function of θ2, which is my second objective, and θ1, which is the uncertainty in the power demand. Okay, so the key message that I have tried to convey is that typically we have been looking at energy minimization problems and environmental impact minimization problems in isolation, but they are connected, okay? And they're connected through a multi-objective framework. And on top of it, there is this effect of uncertainty, which makes the solution of these problems even more complex. And as we move forward, there are social and governance impact or factors as well, which are usually not taught or discussed in much details. But the future generations are going to be very careful about this. Whether you put a new chemical plant in a green field, or where you would think that it would does not look nice, people are becoming more and more aware of it. So we need to take into account the social acceptability as well, and obviously governance factors, the regulatory bodies, and so on. They impact these decisions as well. And while we continue to develop new technologies such as based upon renewables, we need to keep in mind that it is a systems problem where all these factors and issues are interconnected. And I have presented 2 approaches based upon first principles model and a data-driven approach, which feed into an overall multi-objective optimization under uncertainty framework. And this is also amenable for looking at more sustainable technologies as they are getting developed more and more. And with this talk, I will stop sharing, and thank you for your attention. And we'll be happy to answer any questions that you might have.